Hello students, here we're going to be looking at optimization. This is one of the main ways that we use derivatives in a context outside of math. As usual, your Khan Academy stuff is going to be on your own Jamboard for this. Alright, we're going to start off with looking at some tables and talk about what they tell us about some graphs. Alright, we're trying to find some absolute extrema. So these are the highest points on all of our graphs, and let's just talk about that first. Okay, so absolute extreme we got to be a little bit careful of. We've got to check endpoints because they might not show up as derivatives. And when I look at my endpoints for this graph, we're told that f of 0 is 0, f of 3 is -2. So at a minimum, we've got 0, 0, and 3, -2. Okay, now let's find some other things. So the first thing we have to identify are some critical values. So we're looking for places where f prime of x is equal to 0 or f prime of x is undefined. All right, in looking here, we've got two of those places at x equals 1 and at x equals 2. Those are places we have to consider in terms of checking out whether or not these are absolute extrema. All right, so what I'd like to do is to kind of take a look at the bottom chart, and looking at this bottom chart, we're going to get some information about this graph. The first thing I notice is that between 0 and 1, our graph is positive. Between 1 and 2, our graph is positive. And between 2 and 3, our graph is negative. So to me, that tells us that at 2, our graph crosses from positive to negative in some way. We also know the derivative does not exist there, so there's something happening there that's an issue. Okay, now I'm going to look at my derivatives. So between 0 and 1, we are increasing. And then between 1 and 2, we are decreasing. And between 2 and 3, we are decreasing. That tells me a couple of things. First, it tells me that f of 1 equals, in that case, 2, is a max. And with regards to this situation, that's going to be the absolute max. That's the highest point that we achieve. Before this point, we're increasing to that height. After this point, we're only decreasing. So that's going to be what's going on there. The second thing that we've got is f double prime. So this tells us this is concave down. It's going to have some kind of a shape like this. And then still concave down here. So this could be something like this. That might be why we have an issue there for our derivative. But that's also not really something going on as far as a max or a min, so we don't really care. So my absolute extrema, my max is at 1, 2, and my minimum is at one of the endpoints at 3, -2. Points of inflection require us to change concavity. This is negative the whole time for the second derivative. No points of inflection. Sketch a possible graph of f. I kind of did that by accident as I was going into there. The key things are positive value, increasing and concave down. That's what this looks like. Positive value, decreasing, concave down. That's what this looks like. Negative value, decreasing, concave down. That's why that goes like that. So we have to have a 0 at x equals 2. In fact, we're told that with the table as well. I didn't bother to look at that. All right, same thing. Now we're being told that we've got an even function. What that suggests to us is that this graph is symmetrical about the y-axis. So whatever we have here, the same thing's going to happen if I go to the points -1 and -2. All right. I'm assuming that we're going to be asked to find the same three things, but we're not listed that here, so we're just going to do that. So extrema. And here our endpoints are at -3 and +3. We don't have that info. So one of the things I've got to be a little bit careful of is to take a look at what's going on here. And going from 2 to 3, our graph is increasing. So the only thing I can really say is that f of 3 is greater than f of 2, because our derivative is positive between 2 and 3, and therefore we are increasing. I'm also going to use that going backwards because this is an even function. That means we're symmetric. That f of -3 is going to be greater than f of -2, and that those two values are also going to be equal. So just to kind of keep that in mind. All right, I'm going to put my other points in my table because I like making my own tables even if a table exists. So -2 is going to be the same as 2. -1 is the same as 1. 0 is 2. All right, so that's what we've got so far. And I'm beginning to see some stuff going on here. I also didn't bother to do 1, 0, and 2, -2, which are the actual ones that are in the table. And I also like that I have -2 when that's clearly not even an option. That's -1. Okay, so now that we're in that shape, I begin to kind of see some things happening here. Okay. Let's take a look at the derivative stuff, and I'm looking for critical points. I've got a critical point at all three of the values that we're told, so 0, 1, and 2. We are continuous, so we don't have to worry about that being the issue for derivatives. That means we've either got some kind of a pointy thing, or that we have some kind of a weird thing happening as far as derivatives, like we have a vertical tangent line or something like that. So the same thing would be true at 0, -1, and -2 as well. Okay, I'm going to now look at my derivatives. We are negative, negative, positive. That means that we're decreasing, decreasing, and then increasing. And looking at my values at 2, we're at -1. And if we're going down to that point and then going up in both directions, to me, that tells us that -2 and 2 are the absolute mins. The absolute max issue is a little bit trickier because we don't really know. When we're looking between 2 and 3, we know that we're negative, okay? We know that the slope is positive. Oh, and I guess that, okay, that is going to let us know. And because even up to the point that we get to 3, we're negative, means we're never going to get higher than 0. So I'm going to put an addendum here and change this so that they both, since they're both going to be the same value. Oh boy, there we go. I'm making a mess. So I'm going to say f of plus or minus 3, because those would be the same value, must be less than 0 and must be greater than f of 2, which is negative 1. And I know that because of the two pieces of information. The first is that the derivative is positive, so we've got to be increasing from a low of negative 1. And the second is that our value is negative, so we're below the x-axis and never actually getting up to 0. That also means to me that there's no way that this cannot be either a max or a min, because we have values that are lower than this and values that are higher than this. So our max is going to be at x equals 0 is our absolute max. Points of inflection. I'm looking for where the second derivative changes sign. Between 0 and 2, we're changing sign at x equals 1. We've got a 0 there. I like it. X equals 1 is going to be a point of inflection. This graph, I'm going to draw half of this first. So we've got 0, 2, 1, 0, 2, negative 1, and then 3 is somewhere in here. So that would be concave down. This part is going to be concave down and also decreasing. That makes sense why we don't have a derivative or second derivative there. That's a pointy thing. And between 0 and 1, we are decreasing and concave up. It's going to look something like this. That also means that the other half of this graph is going to mirror that and look something like that. F of 3 and f of negative 3, that's about as much as we can conclude. Can't really do much else beyond that. So we've been talking about max and min things, and in looking at this, we're going to find ways to maximize and minimize stuff like areas or volumes here. And the hardest part for most of my students tends to be based on not the calculus, but rather the algebra and kind of setting up problems. So I'm going to spend a little bit of time on that. I'm going to talk about how we think about maximizing things and kind of a process for here. So the process for all these is going to be pretty similar. We're going to set up our equation. For maximizing or minimizing something, we're going to take the derivative, and then we've got to find critical points, just like we were doing for the chart things we were looking at a few minutes ago. And then we got to check those points to identify if they are max or min values. So if we've got largest possible area for a right triangle, okay, I'm going to say, so my setup, A is equal to base times height times a half. Hypotenuse is 5 centimeters long. All right, that's kind of annoying. So we've got 5. If I call this x, I'm going to have to use the Pythagorean theorem to get that other side. That would be 5 squared minus x squared. Cool. All right, I'm going to plug my stuff in. We've got area equals x times the square root of 25 minus x squared. And that's all going to be over 2 because the times a half part. To maximize this, we then have to take the derivative. So this is going to be a product rule. It's also going to have a chain rule as part of that. I could do some stuff to make that a little bit less gross. One of the things I could do would be to move this back inside the square root. And that's going to end up being something like 25x squared minus x to the 4th. Because I could factor an x squared out of both of those. That would put an x out front. And this is still over 2, which doesn't matter so much. Still have a chain rule here, but now I don't have a product rule as part of this problem. So taking the derivative, we've got 1/2. Square root's going to end up on the bottom. We also have the times 2 on the bottom. Don't want to lose that. 25x squared minus x to the 4th. And then on top, we're going to have the derivative of the inside. So that would be 50x minus 4x to the 3rd. Oof. Cool. All right, so now I've done the setup. I've done the derivative. I need to find some critical points, places that are either 0 or undefined. Numerator gives us the 0 thing, so I'm looking at 50x minus 4x cubed is equal to 0. That tells us that we've got 2x and then 25 minus 2x squared. That would give us an x equals 0, which doesn't make sense for a base. That also would tell us the minimum, in case you were curious. And then we've got 25 minus 2x squared is equal to 0. That's going to give us 25 over 2 plus or minus the square root of is equal to x. Because we're dealing with lengths, the negative square root does not make sense to include. But I've got this 25 over 2, the square root of that, as an x value. Okay, then I've got to look at my undefined places. That's what would make the bottom 0. So we've got 4 square root's 25 x squared minus x to the 4th. I lost a 5 in there. Is equal to 0. In short order, that's going to give us x squared 25 minus x squared is equal to 0. X equals plus or minus 5, only the 5 matters. And that might make sense because we can't have a leg that's the same as the hypotenuse. So the undefined point doesn't matter for that either. We still have to check it just to make sure. Okay, so we've got one critical value left, and that's the critical value of 25 over 2 square root. And what I'd like to do is kind of, and by the way, I'm going to write that as 5 over the square root of 2. I'd like to see kind of what happens there. So if I've got this value, and I've got my area formula, which is super pleasant, I'd like to check a couple of things. One is a number that's bigger than this. I don't really love the numbers that are here. 5 over the square root of 2 I know is going to be bigger than 4. Sorry, it's going to be less than 4. So I might try 4. I can't try 5 because that's going to break this thing. But if I try 4, we've got 4. I'm going to go in here. So 5 over the square root of 2. So we have a 0 there. I could also do the second derivative. I don't really want to deal with that here because this is already kind of gross. So if I plug 4 in just to kind of check to see what happens, we get 4, 25 minus 16 is 9. 4 times 3 is 12 over 2 is 6. And I just realized that I plugged that into the original function, not the derivative. Oh man, I'm having a day, huh? Okay, so we got to plug it into our derivative. We're going to have 50 times 4 is 200, minus 4 times stuff is going to be 256. Negative up top. No way to get a negative on the bottom because I can't get a negative with positive square root stuff. So we have a negative value. That means that from this point we're going down. Okay, I also know that 5 over the square root of 2 is bigger than 1. So if I plug 1 in here, we check the same thing. 50 minus 4 is going to be definitely positive. Positive over positive gives me a positive value. That means here we're going up. I've got a maximum x value of 5 over the square root of 2, which you might recognize as being a 45, 45, 90 right triangle, which means my other dimension would be 5 over the square root of 2 as well. Looking at the dimensions of a right circular cylinder, I just want to think about this. So cylinder, we're looking for volume. That's going to be the base area since this is circular. So pi r squared times the height. All right, that's what we're trying to maximize in a sphere of radius 10 centimeters. Oh boy. So I'm going to do a great job of looking at this. So this is a slice of the sphere right through the middle. I did that just so I could kind of get the biggest point. And we need to find both the base. I'm going to do this as a base, and that would be the diameter. And we need to find the height for this as well. We're told that the radius of the sphere is 10 centimeters. I'm going to go out to this corner. And in doing that, we might begin to see some stuff going on here. So again, coming out of this, this would be basically, we're going to try to draw this, something that looks like this. And right now we're looking at just the slice through the center of this to try to kind of see what's going on here. So we've got 10 there. This looks like this would be some kind of a squishy thing. I don't really know for certain. We've definitely got an isosceles triangle going on there. And in fact, the more that I think about this, I think the more likely that this is going to be some kind of a really, I'm going to use the phrase cubic cylinder for lack of a better phrase, because that's going to maximize both the height and the base area at the same time. By the way, this problem goes way above and beyond anything you'd ever be asked to do, just because there's a lot to kind of get at this thing. But in trying to make some sense of this, we can end up getting to some kind of value. So that would mean that the height is going to be 10 over the square root of 2. Oh, but we're trying to maximize this, so never mind. Sorry, I just went on a tangent that was totally unnecessary because I was trying to do that without actually doing the calculus. So, would it be fair to say that the base diameter, which I'm going to call B for lack of a better word, plus the height diameter squared is equal to that hypotenuse squared? So that would be 20 squared. From this, I kind of like the idea of finding this r squared thing because I have stuff that's squared here, and that might mean that I don't have a square root, which I really don't want to deal with. So I'm going to solve for the b. That's going to be 400 minus h squared, and then that whole thing is square rooted. To get the radius, so that was the base diameter, I've got to divide this by 2. Making my equation so we said that was 400 minus h squared. That was in a square root over 2. Squaring both of those gets rid of the square root and makes the 2 a 4. And then times h. From here, we can then do some of that stuff, take the derivative, find critical points, and check those values. Again, I mentioned at the start of this very, very long page that the challenge here is much more about the setup, and in most cases you're not going to have to do that. The calculus stuff is take the derivative, find critical points where the derivative is equal to 0 or undefined, and check those values to see if it's a max, a min, or neither. Okay, to summarize, because again, those were like pretty brutal examples of problems. So a strategy that we can use, hopefully the setup is given to you. If it is not, we have to set up some kind of an equation for what we're maximizing or minimizing. We've got to take the derivative. That's always going to be a thing because the idea here is that when the derivative is equal to 0 or when it's undefined, we have these things called critical points or critical values that we can then check to see if they are max or mins. I'm also going to add one warning here, and that's to check your endpoints too. Because we're dealing with things in a real world, we tend to have values that the real world tells us we can't go beyond. For example, if you're trying to find the best way to get from point A to point B, the longest possible path would be along these two legs of what could be a right triangle. You can't make a path based on this setup that's longer than the maximum length for that. Depending on, so it's a stupid example because I could totally go like beyond this and then double back, but we're not going to go there. I can't make a path that's any shorter than that hypotenuse. So we have some limitations in the real world that involve lengths and things like that. We can't have negative values. We can't have, some cases, positive values depending on what we're talking about. So we do have to check some of those values. We've got some options for optimization practice. Again, mostly we care a lot about derivative critical values and check your work. See what those critical values are. The setup is really challenging for most of the students that I have. And again, given that this is a calculus class and you're going to be assessed on calculus knowledge, that's kind of the limit of what we're looking at.